Hot molecule to water and it exploded in his face, and after he got back from the hospital he put the bottom molecule in water, and he was really surprised that the bottom molecule didn't explode also. Help Joe out, help him understand why he was at the hospital that day.
He wasn't working in a pink coat.
He wasn't working in a field, but most definitely he probably wasn't wearing a lab coat or safety glasses. Yeah. He's a bad boy. But chemically, why did he get an explosion with the top molecule? Michael?
The top molecule, well, it's, the carbon is more positive and more reactive.
Okay, so you're giving me an inductive argument that this carbon is more positive than the bottom carbon. So the way I'd phrase the question, please explain to Joe the chemistry behind why the top molecule was really reactive towards water and the bottom molecule wasn't. In your answer, tell Joe about reaction kinetics, stability, energy, something like that. Okay, so there's a start. Something about positiveness. Anthony, did you want to take a shot?
I was just thinking, like, chlorine's it's a better leaving group, so it would happen faster.
Okay, so better leaving group. Why is it better? It's electron negative. Yeah, I don't know. I'm not sure that I buy that.
Not as strong.
Okay, all of this is fine, but leaving group assumes rate determining step. Is the rate determining step this thing falling off? I don't know. Isn't something about stability what we want to be talking about here? Resonance. What makes this guy so darn stable and unreactive? And how?
Because the lone pairs form oxygen and push down.
Say that one more time.
Like how is the resonance?
Yeah.
Well, the oxygen double bond can move down to nitrogen.
And how does that happen? You're right, the double bond switches location, but how does that happen?
The lone pairs of nitrogen will lead to the carbon bond.
Good.
And
Okay.
the oxygen will push up.
There we go. I thought that you were saying that double bond moved down here, which would not be good electron pushing. But yes, these are resonant structures of one another. Okay, getting a few more points here. There's a resonant structure for the bottom molecule. Don't we have a resonance structure for the top molecule too?
Yeah.
You know, let's go ahead and draw that one. Okay, we're looking a little better. Maybe as part of my question I should say, you know, show Joe some resonance structures. Talk about stability, reactivity, help him out. So you got a lot more points now that you drew the resonance structures for the molecules. But what else can we say?
Well, that's a bad resonance structure.
The top one is top right is a bad one. Why is that?
Chlorine has a like positive proton.
So this is a poor resonance structure. It doesn't contribute as much to the resonance hybrid. How about the one on the bottom?
It does.
Now they both contribute, don't they? Pretty significantly. All right, so what?
It makes it more stable and a slower overall reaction.
Okay, so this resonance here makes the amide more stable And as a result, it's less reactive towards water. Okay, I like that. What does this resonance structure do to the carbonyl group? Does it make the carbonyl group electron rich or electron poor? Makes the carbonyl group's electron rich. Is a nucleophile going to want to attack this carbon very easily if the carbonyl group is electron rich? No, this is going to be a weaker electrophile. This electron donation makes the carbonyl group a lot weaker electrophile, which is kind of where we came back to. Here you said it was more positive. Here you said it was less positive. The reason comes from A, inductive effects, and B, resonance effects. So you should include both of those in your answer.
Yeah,
James.
why is it less positive? So, because the oxygen has a negative charge.
Yeah.
Is the nitrogen also like, now you have a positive nitrogen, it's like pulling electrons?
Yeah, you do. The next step would involve a nucleophile attacking the carbonyl group. So our actual mechanism, nucleophile attacks the carbonyl group. This second resonance structure makes the carbonyl group extra electron rich, so the nucleophile can't as easily attack it. David?
If you drew one of those cross arrows on the bottom one, it would still be more positive on the carbon though, but like to a lesser effect? Or do you think it would?
I'm not sure where you crossed arrows.
One of the
oh,
yeah, the indicator.
dipole moment.
Dipole, yeah.
Yeah, the dipole moment. This would be a weaker dipole,
Okay.
which means that the carbon is more electron rich or less electron poor, less positive. Chlorine will make the carbon more positive. Is that okay? All right, I saved the synthesis for last.